at least two more session for or three for the chapter 15. I try to finish all the way 15.7, 8, and 9. I will try to finish that today. So I hope I can finish it on time. But I want to have some exercise, but I think I will just give you some notes and maybe another recording so that you can have more details on how we are going to use some of the formula for your exercise. Okay, the last time we have learned until the triple integrals in the cylindrical coordinates. Okay, so cylindrical coordinates, we are noting, we are writing the coordinate as r, theta, and z. So basically, what cylindrical coordinates means is you will have a polar. Okay, you will have a polar. So this 2 is a polar with some surface level, right? Surface level z. Basically, it's the height, right? Okay, and if you want to evaluate the integral, let me show you how. Okay. So how to evaluate in cylindrical. Okay, so basically, this is the general equations. Let me write the triple integrals. This is L, M, N. Okay, and then you have the X, Y, and Z. And then the idea is, of course, the difference will be on the volume, the delta volume. So in cylindrical, so let me write the volume is actually area multiplied by height, right? So because we have done in polar, so the area will be the polar, which is in our terms now, the polar becomes Ri, delta Ri, and delta theta J, right? I believe we have learned this, we have discussed this, like the polar, and the height is just delta Z. Okay, so basically, this triple integrals. So these two integrals here, it will be the double integral, the polar double integral, and this will be Z. Okay, so what we are going to write, so we will have the functions here, r, theta, c, and then we will have r, right? This is usually becomes r dr d theta, right? But here we will write r because it's z first. We write dz and then the r d theta. The rest, like the r d theta here, it's the same as in polar. So this will be theta here, and this will be r, the second one. Okay. Okay. So whenever you find, let me draw some illustration for you. So whenever you find any functions that or many, if you want to evaluate the triple integrals, and you know that the boundary for that integrals in some plane or in maybe in XY plane, or maybe in other plane, they are creating a polar relations, then you can take them into cylindrical coordinates. For example, if you have this surface here, and by doing this, you can see that it's actually making an, a polar relations. So here's theta alpha, and here's theta is, let's say, beta, and also we have two radius. So this radius is r2 and r1, right? And we can take this radius in terms of functions of theta. Let's say theta, h1 theta, and the r2 is h2 theta. And z itself, it's the functions. So z is it's having two surface, lower and upper, with two variables. Okay, so this polar part here is the area, and this is the height. Okay, so z will be in, so we will have triple integral, okay, from alpha, beta, and then from r1, let me write r1, and then r2, and then z here, z is u1 and u2. Maybe if you are having any function here, r, dz, dr, d theta. Okay. So this will be the general terms that you might have. Okay. So the idea is still the same, same as the, previous triple integrals. So first, identify the surface, the upper and lower surface. This is the u2xy and u1xy, but actually it can be in any axis, like for example xy, yz, xz, right? And then of course the second one is you need at least to make the 2D sketch for its projections. Okay, this is to determine the double integral, right? To determine the polar bounds r and theta. Okay. Sometimes you can also, if it is quite simple, you can draw the 3D the 3D graphs if you want, if it is quite simple. But if not, then at least try to make the 2 dimensions sketch for the graph. So let me give you example. Okay. So you have this triple integral where g is within this cylinder below z equal 4 and above z equal 1 minus x squared minus y squared. Okay. Now first, the question itself, it doesn't have any function here, so that's okay. We just evaluate the boundary, and then we can just integrate directly. Okay. Okay. Now, I think this is cylinder, and this is becoming the parabola, right? If you would like to see the which with each x and y is 0, you can have this and this, right? Which is both are parabola, so it will be a paraboloid, right? Okay. I think it's quite simple to draw the 3 dimensions, so let's draw the 3 dimensions. So you can see what kind of volume we will have. Okay. The first is the cylinder. I will draw the cylinder here, probably here, and then take some maybe if this is 4 here, so this will be the boundary. So I will take this cylinder. Okay, so that's our cylinder. Okay. Okay, and then the other cylinder, like that. Okay. This parabola, this is C, Y, X. Let's take Z and Y. So we will have this parabola, and we will have the XZ, and we will have this parabola here. So imagine that this paraboloid here is like a cup, right? So the volume will be in between this paraboloid and this plane z equal 4. So in between here, this is our region. Okay, and how do we write? We can write, for example, let's write the xyz, and let's start from z, because z is our function with 2 variables. So z is start from 1 minus x squared minus y squared until 4. Okay, that's our z. And then our y is, we can start from here. The y is plus minus, right? And we can write the y from minus until the positive 1. And then the rest is the x. The x is, this is 1 and negative 1, right? For x, because the radius is only 1. So it's from negative 1 until 1. And then dv, then this will be dz, dy, and dx. Okay. So of course, if you want to go for this, like, you can try to solve it, but I don't think you can solve it easily by doing the regular triple integrals. So I'm going to do now is convert to cylindrical. So xyz going to be r, theta, and z. Okay, now if you look here, this z, we can write z as, right? So let's do that. And if we look at the circle here, the theta is from 0 to 2 pi, and the radius is just 1. So we can just write r is 0 to 1. So we can write the volume 0 to pi, 0, 1, and then 1 minus r squared until 4. And then this will be r, dz, dr, d theta. And we can solve it, I think, easier than this form here before we convert. So the inside integral become ZR I think we can integrate directly 2 pi, and then you have 4 minus, and then r, and then dr. Okay, I'm integrating d theta directly. So 2 pi, it's 3 plus 3 plus r squared, and multiplied by r, it's r cubed dr. So I will have 3 over 2 r squared plus so 2 pi multiplied by 3 over 2 plus 1 over 4 is 77 over 4. So it's 7 over 2 pi. Okay, that's the one example. Okay, another example is a little bit harder than the previous one. So let E be a region inside a sphere of radius 2. So the radius is 2, centered at origin. So the sphere is on 0, 0, 0. And above plane z equal 1. Okay, so E is inside the sphere, but it's above the z equal 1. Okay, so for z, you need to have 1 until this sphere equations, right? Let me draw for you. Find volume. Okay, find volume of E. If we draw, let me draw the sphere. Okay, that's the sphere, and let me draw the plane. Maybe 1 is here. So because this is 2, so 2, negative 2. This is 2. This is also 2. Okay, let's say this is 1 here. So maybe I'm drawing a line like that. And because it's sphere, it will cut the sphere. So I will make it circular here, like that. Okay, like when you have maybe like you cut them and you have this kind of shape, right? And when you project this to the XY plane, you can see that it is creating something like cylinder for this part, right? But you can see the circle here, right? Okay. And where is our E? Our E is on this part. So from Z, this is Z equal 1. Okay. So what can we do now? First, what we can do is we need to write the sphere equation first to define the functions. Okay, the functions for the surface. So the sphere is radius 2, so 4. And then we can define this sphere into z. So it will be plus minus 4 minus x squared minus y squared. Okay, that's our z. And this is for the so z equal 4 minus x squared minus y squared. This will be the upper surface, right? As we discussed previously. And then z equal 1, the plane, it's become the lower surface. Okay. And then at this line here, if you look this line, the purple one, and you look at the green color that circle around that line, that is actually a circle, right? So this is a circle. X squared plus y squared is equal r squared. But what is our r? Because it's equal 1, z equal 1. So and it's on the sphere. So what we can do is actually x squared plus y squared plus 1 is 4, right? At z equal 1. So x squared plus y squared is actually just 3. So we now notice that this r is square root of 3. Okay. And then we can set up the integrations, okay, and then make it this z into a polar part. That is our polar. And then we can see our circle here. That is the circle, because we want to evaluate all this volume, right? So the purple one, we want to evaluate that. So imagine that we're going to look at the circle, and we can see that it's a full circle, which means when we write the polar, it's from 0 to 2 pi. And then the radius, okay, the radius is from 0 to square root of 3, right? If we just look at that shape, only this, right? And then the z is 1 to 4 minus r squared, right? From z equal 1 to this surface, the sphere. Okay, and then r dz dr d theta. And then you can solve this by yourself. I believe it's not too difficult to solve, I think. And that is our volume. Okay. So you can actually convert many functions if you know the relations with the polar. Okay. Like for example, if you know that it should be a circle, then you can definitely convert into cylindrical coordinates in triple integrals. Okay. If you have any questions, please chat on the chat box. Please write the question if you feel confused. Because today I will be a little bit faster. Okay, sorry for. You can review on the recording if you want. Okay, the next part. Okay, after the cylindrical, there is also another method. It's called the triple integrals in spherical coordinates. Okay, the difference between cylindrical and spherical is on how you write the main component of the functions. So this is x, y, z. And let's say we have, usually we have the polar here, right? The radius, and then we have the this is sorry, this is theta, and then let's take up there, and then the difference between polar, we have two angles. Okay, so another angle will be wait, another angle will be here, psi. Okay, so if you look here, you will have point P. You will get the radius will be determined by this radius. It's called rho. Okay, and this is the coordinates rho, and then theta, and then psi. So if you can imagine what this looks like is actually, I will maybe draw another picture here. Okay, so let's say you have a sphere. Okay, let's say you have a sphere. Imagine in this sphere, you can put any point you want. Okay, maybe here, up here, this point P. Actually, this point P here is what this the same P here is all about. Okay, this is actually a sphere that you can pinpoint on any its surface. Okay, erase this. Okay, so in this case, the radius is always positive. Okay, because it's this scalar, right? And then the theta, it's full circle, right? It's full circle here. So you can write in terms of 0 to 2 pi. And then you can also write the psi. Now, the psi here, this is only from the, we can only see from Z. It's just up until here. It's not a full circle, okay, because it's not defined the sphere, if you can imagine. So the size only have until pi. Okay. And imagine if the radius is a constant, not any constant, of course, this will be a sphere, right? With the same radius. Like this is rho. So everywhere in the surface is same radius, right? It will be the same. Okay. And if the theta is a constant, then you will have, okay, you will have, if you look at maybe theta is here. So it will be a plane. It will be a plane. It will be a plane here. Okay, if theta is constant. If psi is a constant, what will happen? So let's say this is your psi is there. So imagine psi is there, and then all the other is not a constant. So it will be creating a cone, right? Creating a cone. Or precisely for this case, it's a half cone. Okay? Now, how do we write the coordinates? Okay, how do you rewrite these coordinates? How do we convert them? Okay. Okay, let me write some notes here. For polar, you remember that we have this condition. Okay, now observe this part. Okay, observe this triangle here. Okay, let me make the triangle. This is also psi, right? So I will write this as psi. And the bottom is, this is the radius r, okay? And this is the rho. And the height, I will just write z, okay? Okay, now we can write z in terms of rho. Rho cosine psi, right? And r will be rho sine psi, okay? So if you maybe confused or forget, you can actually write down the conversion through this triangle here, okay? So write down this, and then you have also the sphere equations, which is this, okay? X squared plus y squared plus z squared equal r squared, okay? Okay, and by doing so, you are writing all the terms now. You have the z, you have the x, you have the y, okay? And because we are getting rid of r, so our r will be changed to this. So our x will be rho sine psi cos theta, and y will be rho sine psi sine theta. Let me write z maybe here. I will write again here. So this will be our main conversion for this spherical coordinates. Okay. Okay. Now, the question is now how to evaluate the triple integrals, right? And this is quite complicated, but I think we can make it. So let me write this. Okay, imagine this is a part of a sphere. Okay, so if you can imagine, this is a sphere. Okay, and you are cutting up this surface here, and imagine the uh, the sphere itself, it has the some thickness. Okay, so this is the thickness here. Okay, now if you look here, we can see that inside we will have a difference, right? This is the side first, different inside for this side, okay? And we can also find this side here. We can write this. This is basically from from the R. So we changed our delta theta into this. And then we can also find this part is the delta rho. Okay. So the volume from this part of rectangle, because it's very, very small, we can write them or approximately delta rho. And we can write it's become rho I squared sine psi, and then delta rho, delta theta, and delta psi. And then this will be the conversion, and this will be the differentials, right? So the rho, the theta, the psi. Okay, so we can write triple integral for spherical coordinates. So let me write completely f. It should be xyz because we already convert them into our sphericals, it will be rho sine psi cos theta, rho sine psi sine theta, and then z. Z is rho cos psi. And then you need also to write this conversion. So right here. So rho squared sine psi, the rho, the theta, the psi. And then maybe we can write this as from C, D, alpha, beta, A, B, with the E is basically rho, theta, and psi. We can write this from A to rho to from A to B for rho, and alpha to beta, and then C for psi, and until D. Okay. Now that is the term for the spherical coordinates. Okay. And actually, that will be our. So whenever you have a function here, any functions like x, y, z, but you know that you can convert them into the spherical. Maybe you think that it will be much easier to convert to the spherical. You can do that, but don't forget to multiply with this. For example, if the functions you have, the functions is something like this. So what will you do here? You want to integrate one by one? It's difficult, right? It's better to just convert them into rho squared and then 3 over 2. So it will be E rho cubed. At least this is much more simpler. It's easy to be converted. So you can convert them, and then don't forget to multiply with the rho squared sine psi. And then you can do the rest. Okay. So every time you see any functions that related to sphere, basically you can convert them to spherical coordinates. Okay. I hope you get the idea. So, but I don't think I can tell you in more clear like the proof or anything, but I think from what we have done here to at least make a new coordinates in which compose from rho, theta, and psi. I hope you get the basic idea from here. Okay, and then the rest is just need to look at the triangle here, and then this one is the important one. Okay? What you're going to do from here is the r you're going to substitute to here, and that is why you have this. Okay. Okay, I hope you get the point for the spherical coordinates. Okay. Um, I don't think I have time to give you some example from here, but I will give you maybe another homework to work with, and then I will give you the solution on how we are working on that. Okay. Okay. I will move on to the next section that is about the last sections in our course. It's actually called the change of variables in multiple integrals. Okay. Okay. Remember that in double integral, at the very maybe early part of our chapter here, we have learned that we can also convert this to polar, right? Let's say this is becoming r cos theta, r sine theta, and then this is r dr d theta. Okay, so we can convert, right? Now, in this chapter, in these sections, we will learn how do we get r, okay, from one theorem. So imagine this is you are going to convert from rectangular coordinates to the polar coordinates. Okay, imagine that. Sorry. Okay, it's okay. Imagine this is having a transformations. Okay, from R to S. The boundary is changed, right? Okay. Uh, in general, okay, let me write in general. Consider T is a transformation. So when you have T, you can convert the variables u, v to x, y, where x and y is actually functions of, both are functions of uv. Okay, let's say we have those functions. Or sometimes you can write directly like this. That's also okay. And assume that t is c with apostrophe 1. This means that g and h both have continuous first order partial derivatives. So you can uh, derive them. Okay. let me maybe write the. Okay. Okay, maybe this is the UV. Okay, this is UV. So this is U and V. So we have an axis. And let's say we have the region, its region is S. Okay. And this part here, let's say R, and this is XY. Okay, now we can take this as the transformation or take this as its inverse. Okay, so we call maybe writing more details U1 V1 to make it clear that that is a point on some clear coordinates. Okay, so from here, what you can conclude is x1 y1 is the image of point u1 v1. Okay, uh, if this is clear, if this is the transformation, so we write the transformations like this. And if no two points have the same image, meaning that t is 1 to 1. It's similar meaning to 1 to 1 functions, in which you can have the inverse from 1 to 1 functions, right? So t transform S into region R. Okay. And then if t is 1 to 1 transformation, so it has inverse. Okay. And then we can have u in terms of so we can convert back to the xy from u using the inverse. Okay. Okay. Let me give you an example, and then what we can conclude from the example. Okay, let x is u squared minus v squared, and y is 2uv. Okay. So if we need to find image, okay, of square s, this is uv, and it is from we can set up the boundary from 0 to 1 and 0 to also 1 for u and v. So what we can solve from here. First, we can draw the u and v. So we can draw this, okay, and we can set up a boundary. Maybe that is our boundary. That is 1, right? And this is the square, right? Image of square. So this is 0, 1, 1, 1, 1, 0, 0, 0. So okay. So this will be our S. Okay. So this will be, let's say, S1, S2, S3, S4. Okay, now based on all these points here, we can make a new xy, right, from these relations. So we will have, okay, for, or maybe I will write the coordinates first. So first is, if we have, let's see the first side. Okay, the first side, given the v is 0, okay, v is 0, and we will have x is u squared and y is 0. Okay. And then second side, u is equal 1. Okay. This one. Okay. So this is first side, second side. U is equal 1. And then we can get from the equations, u is 1. So 1 minus sorry, v squared. And y will be 2v. And we can set up this and solve this. So v is half y. So x is 1 minus y squared equal over 4. Okay, this is for x from 0 to 1. Okay, which is this is a parabola, right? And similarly, the third side, when v is 1, you will get, this will be u squared minus 1. And similarly, you will get the x is actually y squared over 4 minus 1. Okay. This is from -1, x 0. Okay. And the last one, I forgot the fourth side. It's u is 0, then x is negative v squared, and y is 0. So it will be from -1 till x until 0. So we will get from this square, we can convert um, to xy positions. So this will be x. Okay. And this will be 1 minus y squared over 4. This should be just line from -1 to 1. This is 0, 2. And this will be our region R. So this is having a transformation from there. Okay. Now it seems what we are doing here is really tedious, right? It's depend on the functions, and because the functions is not too complicated, right? We can try to take sometimes and then try to imagine what it will be looks like. Okay, but what will happen if the functions is getting more complicated. So we need to have a standard procedure or maybe general rules for the transformations. Can we make these transformations into some general formula? Okay, like we have in the previous, in the polar, we have general formula that you need to multiply with r. How can we get this r, right? In general formula and maybe other formula as well. Okay, it takes some time to see and to prove the formula. But what can I say here? I hope we have time. Is that if this is the u v, okay, this is square. Let's say we have, this is delta v and this is delta u. And let's say we have the initial point u0, v0. Okay, and this is when u is equal u0, and this is when v equal v0. Okay, and then we are going to have a transformations to our functions x and y. So we get, let's say we are having this kind of uh, shape here. Let's take this is x0, y0, and take this r, u0, and v, and this also r, u, and v0, and this is the region r. Okay, and r, from there, r is actually function and become a vector functions. Okay, and then if we remember, we can partially derive this, become ru, yeah, maybe I will write this, or we can write in terms of Leibniz notation. And similarly, we will have RV. Okay. And then we can approximate, if I'm taking this R bigger, maybe here. This is R. So this is R u0 v0, the vector functions. And here is R u0 and then v0 plus delta v. And here is R u0 plus delta u and v. Remember that we can approximate this by this line here. Let's say this is another vector. Let me write this is vector a and b. Okay. So approximate r st s. Okay. So we can approximate a and b to become similar to what we have here. It's a square here, right? So we are going to put the square into the r. So we are going to maybe. So put this maybe this around here. Okay. Okay, and we can approximate this AB, that is the parallelogram. So A is R. This is the length for A, or the vector function defined for A. And then we can define from the limit definitions. If you remember that you can derive this, and because we are actually using the limit concept from here, because it's adding plus some delta, right? So we can add so we can have the secant, right? Or maybe it will be a tangent if you are going to approach. And thus, so this will be concluding that this will be approximately delta U and RU, okay? And this will be approximately delta V RV. Okay, and then because it's parallelogram, the area, or yeah, the area is the cross between okay. Okay, now let me move to the next slide. If you confused, let me know. But you can review later. Okay, so area of parallelogram is okay, or we can write, because it's the vector functions, and we can move the scalar part outside. Okay, now this part we can check the cross. Let's just write ijk delta x du dy du and dx over dv and dy over dv. This is from here, from this part. Okay, and then we get this is delta x delta u delta y delta u delta x delta v delta y delta v, and then this will be on k, because I cross j is k, right? Okay, or you can also write because the results should be the same. You can also write like this, switching the switching this right to here, it's the same because basically this is the determinant, right? The determinant. This is if this is A, B, C, D, this will be AD minus BC, right? Okay. Now, this determinant is called the Jacobian. Okay. So let me write this, and this is the most important. Okay, if you don't know the what's to prove from what I've told you before, don't worry. This is what you need to remember. So definition: Jacobian of transformations D given by X and Y. So this is Jacobian. You need to write this symbol, which means this is, you need to find the determinant. And this will be our Jacobian transformations. Okay. Remember that polar, yeah, the polar part. So if X is D, let's say R theta, this is R cos theta, right? And Y is, let's say, using another function that is R sin theta. The Jacobian will be xy and then r theta. So you need to find, first is the dou x dou r and dou x dou theta, and then dou y dou theta. Okay, let's find the determinant from here. Okay, dou x dou r being derived with respect to r will be cos theta, and dou y dou r is just sine theta. Okay, and dou x dou theta, cos theta derived become negative sine, right? Negative sine, negative r sine theta, and then the r sine theta becomes r cos theta. And what will happen here, we can get the determinant r cos squared theta minus r sine squared theta, or we can have r cos squared theta plus r sine squared theta, in which you can get r. Okay, and what is this r? This r is actually your, so you have double integral. Let's say that's r theta. You need to write r here, right? So this r is the same. So this is actually the Jacobian. That's the Jacobian transformations. Okay. Okay. Now, if we want to look more into the first problem here, let's write our Jacobian. So dou x, y, dou uv. It's more practical if you are just using the Jacobian to check the determinant. Okay, let's see. Let's write here dou x dou u is 2u, dou x dou phi is negative 2 phi, and dou y dou u is 2 phi, dou y dou phi is 2u. And we can plug in all to here. So 2u, negative 2 phi, and then 2 phi and 2u. 2 phi and 2u. We will get 4u squared plus 4 phi squared. And then we can write in terms of if we want to evaluate and R is bounded by x-axis and parabola. This is actually what we have done here, right? The same thing here, the same formula. So if this is the R, okay, so we can just use it for this part. Let me use the new page to solve this. So y is actually 2uv, so we can write r becomes s. Okay, we are going back. So we are going back from uv, from xy here. We are going to back from to uv. Okay. So this will be 2uv, and then the Jacobian, and then the a. Okay, remember that we are going back to s. So we will look here, then all the region is just from this boundary, right? So we can use it to the integration here. And then you can solve it easily. I will take out 8 outside here, and I will get inside will be okay. And integrate u first, so it will be 4. And then multiply 8 to 4 and 2. It will be, and inside putting 1 and 0. So this will be 2 phi plus 4 phi cubed, and then d phi. And then you have integrations one more. So it's 2. Okay. What happened for Jacobian 3 by 3 determinant? So Jacobian for 3 variables, for 3 by 3, let's say U, V, and W. It will be the determinant of the 3 by 3, like in the vector you learn. Okay. And then the theorem will be yeah. So the Jacobian will be the same similar functions that you need to apply. Okay, if you want, you can also prove the spherical coordinate. It takes a while. If you remember the formula or the conversion, and z is rho cos psi. Okay, the Jacobian now we will have the dou x y z and dou rho theta and psi. Okay, first we need to find. Let me write all the things we need. Okay. Okay, integrate x to rho. So rho is just a row there, here, right? So we just have, maybe I need to take here. So this will be sine, psi, and cos theta. And then this will be sine, psi, sine theta. And the rest is for the z is cos psi. Okay, sorry if you hear some noise. It's quite windy in my place, and I kind of insulate the audio from outside. Okay. And then derive with respect to theta. So theta is here. So cos will be minus sine. So minus rho sine psi cos theta. Sorry, sine. And this will be rho sine psi cos theta. And z, there is no theta, so it will be 0. Let me move another. Okay. And then this will be rho cos psi cos theta, rho cos psi sine theta, and this will be negative rho sine psi. Okay. Okay, now we have this 3 by 3 determinant. Okay, if you remember, uh, you can take plus minus plus for the multiplications and take this determinant and then multiply with this, right? And then do the same thing and multiply this determinant with this. But what I want to do is I will pick this 0 here, this below here, the row below, because it has 0, so it will be easy to calculate, right? So we will calculate the determinant will be cos psi, and then determinant of negative row sine psi sine theta. Okay, and then plus going put here, maybe resize smaller. Okay, and then minus rho sine psi sine psi cos theta sine psi sine theta, and then negative rho sine psi sine theta. Okay, okay, I think it's pretty good. Okay, this minus this and this minus this. Okay, cos psi. Now will be negative rho squared sine psi cos psi sine squared theta. And then negative rho squared sine psi cos psi and then cos squared theta. Okay, it's pretty good because it has the same element, right? And then maybe going to the right a little bit more. Okay, maybe there. And then negative rho sine psi rho sine squared psi cos squared theta. And then minus minus, so it's plus rho sine squared psi sine squared theta. And you notice that it has the same same element. Okay. Okay. If we are going to write, we can write this in terms of negative rho squared sine psi cos psi, and then this will be this will be equal 1, right? And then we can write negative rho squared sine psi cos squared psi, right? Yeah, for this part, for the first part. And the second part, we have rho sine squared psi. This is 1, so we have this. So we will have negative rho squared. Let's sine psi and sine squared psi. Okay. We can write this negative rho squared sine psi, and then take this and this will be 1, right? And we will have this, but it's still in a uh, since 0 psi is only this point, and then we have sine it to be positive. So this value should be positive. So that's why we have this. Okay. It takes a while, and okay. Let me check. What else do we need to? Okay, I think we finished this sections. Maybe any questions first? Any questions first? I think we still have some times to. Um, I want to give you some, maybe 1 or 2 example for exercise. Let me check the questions. Oh, maybe. Okay, let me. Time for exercise. Let me give you questions. Let me check first. Question that I think. Hmm. Hmm. Okay, maybe this first. Okay, let S be portion of hemisphere. Let me give you 2 questions. Hopefully, at least one question I can help you solve it. Hmm. Okay, let's just make it. Okay, you can try the first one first. Okay, maybe I will write let E be solid bounded by sphere squared y squared plus z squared equal 4 and cylinder. And by the way, because I have seen the survey that you have filled in, I think our final will be on uh, Saturday. Will be on Saturday, uh, 3 p.m. Saturday. So next week, 26, right? 26th of June, we will have the final exam. Uh, it will be at 3 p.m. The time will be similar to other class, the calculus B class. So maybe the difference is if you start 3 p.m., maybe the other will start 3:20 or 3:30, or if they start 3 p.m., you will start 3:20 or 3:30. And you need to have preparing the paper, and also uh, I think the setup, like the usual setup, like I think the quiz for chapter 12 and 13, like that setup. I will announce in more details later, and also I will announce some homeworks to help you to check all the works, whether you understand or not. I think the last exercise, it's quite good for you, and last quiz also good. I hope you can have similar results on your final exam. Although on the final you cannot open your notes, and yeah, you just need to work out on the paper, and then you need to fill out the form that I will give to you later. Okay, back to the exercise here. I think the first one. Do you get the first one? Okay. This is asking about the area, right? If you remember, the surface of the area will be its double integral, and then it's having a square root 1 plus, this is partial x, right, plus partial y from the functions. And let's say this is this dA, and this d and the a is based on this circle here. Okay, so basically you need to find the partial x from this function, which is, you can treat this as like a squared x. You derive becoming 1 over square root of x, and then multiply with the derivative inside. So if this is negative x squared here, it will be negative 2x divided by 2, right? Okay, and then you get this. And for y is also similar. Okay, so you are using this and then plug into here. Okay, and then because this is a circle, you can convert this to polar. Convert to polar. This is r will be just 3, and then the theta will be 2 pi. Okay, so you will have 0, 2 pi, 0, 3, and then this will be your result from here. And then you need to take the integrations, and if you need to use several methods like USUB or integration by parts, you can do that and find the integrations. Okay, so that's for the first case. The second question, however, it's quite a little bit complicated if you are not really cannot imagine. If you cannot really imagine what the shape it is, um, probably you can draw, because it's not too complicated. It's just a sphere and a cylinder. So this is the 3D section here. Okay, you see x, y. I will give you the clue, but you cannot. But I hope you can solve it by yourself. Let me draw this sphere. Okay, and then let me draw the cylinder. Now the cylinder, it has x and then y minus 1. Remember, in the circle, this is centered at 0, 1, right? Let's say 0, 1 is here because this is 2, right? Radius 2. So this is r equal 2. So you'll have a circle here, and you will have a cylinder. So imagine this is the cylinder here, maybe a little bit higher. Okay. Now the volume E, if we look at, okay, first maybe we can set up the region first. So the region for xy, the region is based on this, right? What can we have from here is maybe we can convert to polar. So convert to polar r theta. Of course, the theta will be from 0 to 2 pi. But what about the r? Now, this is quite trouble for the r. Because if you look at here, the equation here, the r is 1, right? But is it really, can you imagine the what this shape is, okay, from this picture? Okay, now if you look here, squared plus y squared plus c squared, or maybe from here, let me just write from the x squared plus y minus 1 squared equal 1. Okay, let me open all the squared here. Let me expand. Okay, what we can do now, let's convert. Okay, convert to polar. So this will be r squared cos squared theta plus r squared sine squared theta minus 2r sine theta. And then let's find what is the relation between all of this. So this will become r squared minus 2r sine theta. Remember, when you have this in the quadratic solutions, you cannot take this and then this wrong. Okay, what you can do is take this, and now you have, because you have more than one possible answer, right? R can be 0 and r can be 2 sine theta, and which is, this is our r that we are going to look at. So r is a function of theta, so this is from r to 2 sine theta. Oh wait, I think I made a mistake. This is not 2 pi. Do you know why? This is pi. Sorry. Um, do you know why? remember, if you have this 0 and pi, right? Okay, get it? Okay, so that's pi. And then you need to plug in all into the solutions. Uh, let me write this sphere and write in terms of z. And you can write this 4 minus r squared, right? Plus minus, don't forget. So you have triple integral. R dz dr d theta, and then you can solve this. Okay, that's how you solve. I hope you can try this by yourself. Okay, I think I will stop here and I will give you some works for exercise to help you preparing the final. Okay, and if you need to have maybe some questions that you need to ask about the lecture, you can ask through email, or through email, or maybe from the Google Classroom, or maybe just email me if you had any questions, and maybe we can maybe I can help you to solve your exercise as well. So please wait for the announcement. So your schedule for the final exam, it's Saturday. It can be around 3 p.m. or 3:20 or 3:30, around that time. Okay. Okay. What chapter? Oh, good. I haven't talked about that yet. So because we have a lot of sections actually for chapter 14 and 15, so I will limit the the final only these two. And remember that I'm skipping some part, right, on chapter 14 and also for 15. So that just skipping that part. Okay. So you will have like from 15. I think every introduction you don't need to worry about. Both are okay, Doran. You can ask me through GApps or NTSC email. The same. But if you want to directly ask, I think it's faster if you are using GApps. This because the server is different, and because the Google server is better, so it will be faster. So I think some of you are thinking that you are more flexible, or you are getting used to use Moodle, right? Like the Moodle. And we are now using Classroom. So one part that why Classroom is in my opinion is better, they have good server, good connection, and it's more flexible. And again, it give you more storage. So if you are worried about your maybe saving files on your laptop and making it full in storage, you can store in the cloud, in the cloud drive of the GApps. And this is free, right? If you are not using through the NTUSD, you need to pay some subscription, and it's quite expensive. So you need to use the I think the privilege from this school. So that's why I'm happy for GApps rather than the Moodle. The Moodle is slow and it's limited for the storage. You can try to upload some maybe files larger than 100 MB or 200 MB. You can do that. You cannot do that on Moodle. That's ridiculous, right? So I'm happy with the classroom. Okay. And the other thing is, when you are doing submission of your paper, I hope you can convert this to PDF. Okay. But by PDF, I don't. That doesn't mean that your PDF will be like you have 3 pages, and then you are converting PDF1, PDF2, PDF3, 3 files. No, don't do this. Convert 3 pages into 1 PDF. Okay. This helped me to check your answers quickly. Okay. And then do not take picture, and then maybe you have the HAIC file. This I cannot correct this answer. If you want, you can do GPG, but I'm not suggesting this. Please just PDF. It's easier for me. Okay, for your especially for your final. Yes, for your final. So please do the PDF. And in Moodle, I cannot correct your paper easily. In Google Classroom, I can easily correct the paper and then give you a score. Okay. So that's some notes for your final. So final, I will restrict it's 14 and 15. Okay, any questions? You can type in if you want. So if you have you submit your work mark as done? Because I'm always saying that please submit or click the button mark as done, so I know who are in there or not. I've checked everyone, but I'm not giving the score who are not yet submit click button. Please click the button.
Oh yeah. Oh yes, Professor. I
You
have clicked the
already?
button.
Okay. I will check. If not, then I will not give you a score. But I have a score. I have the score.
Yes, I have. Yeah.
Yeah,
Please check again because yeah.
you just submit now,
Ah.
right? Yeah,
Oh yeah.
that's your fault. Okay.
Yeah, but I'm sorry. But
Okay.
yeah, but
Yeah. But I've already checked your score.
yeah, but that mean like could you like double check again because my question is correct, but
Yeah. Of course. All
yeah.
the students I have double checked because the maybe you are worried that, oh, my answer is correct, but why it's wrong? Because the format
Yes.
is different,
Yes.
and that's
Yes.
okay. That's okay. You still correct. I will double check.
Thank you, Professor.
Okay. Okay. Anything else? Yeah, that's okay, Tin. The time for the submissions, it's not like really short. You will have some times to submit. Don't worry, you still have time. Okay. Anything else? Uh, I will stop the recording. If no, then